Now that you're familiar with logistic growth, what we're going to be dealing with is logistic differential equations. At the end of this lesson, you'll be able to solve a logistic differential equation. When we started dealing with exponential growth, we were using a certain formula that we could use to represent exponential growth, and it grew from the differential equation where the rate of change of a certain population was changing proportional to the value of y. So I'm just going to go ahead and solve this normal growth differential equation to remind you of the process that we use to get our equation. So the first thing that I'm going to do is cross multiply. So I'm going to get dy is equal to ky dt. To match my variables up, I'm going to divide by y, so I'm going to get dy over y is equal to k dt. I'm now going to take the integral of both sides. The integral of dy over y will be the natural log of y, and the integral of the right side, since t is my variable, will be kt plus c, 3. Okay, then we're going to do the logarithm loop, so I'm going to get e to the kt plus c is equal to y, and if you recall from previous, we are allowed to put our c out front, so this is really y equals ce to the kt. So when we were dealing with the PERT formula, or actually we used ce to the kt quite often, that's where the formula came from, was from the differential equation. All right, we're going to do that same thing if we start with a logistic differential equation. So notice we still have a differential equation. We still have the population changing at a certain rate. The thing that we added to this formula was we have to take in mind to consideration the carrying capacity, which is L in this case. All right, so solving this equation, here we go. First thing I'm going to do is put it 1 underneath. I'm going to cross multiply. So I'm going to get dy is equal to ky times the quantity 1 minus y over L. All right, I need to get my y's on the left side, so I will do that by dividing. So I'm going to get dy over y times the quantity 1 minus y over L, and then equals k dt. All right, we have our variables separated, so I'm ready to take the integral of both sides. On the right side to take the integral, I do notice that I have a product of factors on the bottom, so I'm actually going to be using partial fractions. So I'm going to get a over y plus b over 1 minus y over L. And then from here, if I get a common denominator, it will be a times 1 minus y over L plus b times y. Those would be the numerators, and then I know that the numerator is going to have to equal the numerator up there, which is 1. And then from here, I'm going to start out by letting y equal 0. So if y is equal to 0, the b is going to drop out, and if I put 0 in for the y here, I'll just get a equaling 1. And then for the second part, if I want to figure out what's going to make the a equal 0, the y would actually have to equal L. So if I let the y equal L, the a's drop out, I'll get BL is equal to 1, which makes b equal to 1 over L. All right, so now we get to take the integral of 1 over y plus the integral of 1 over L over 1 minus y over L. So I'm good to go there, and then it will still equal the right side, which is the integral of k dt. All right, one thing that I'm going to do just to make this a little bit easier so I don't have so many fractions going on in my problem, I'm going to multiply this one by L over L, because I'm allowed to do that because it's just like multiplying by 1. So I'm going to get the integral of 1 over y plus the integral of 1 over L times L is just going to be L. And then in the denominator, I'd have to distribute the L, so I'd end up getting L minus y. And I still have the integral of k dt. All right, so now I'm ready to take the integral of every part. So the integral of 1 over y will be ln of y. And then this one, because of the minus sign, I'm going to end up getting negative the natural log of, when I do this, did I screw up there? Oh, this will just be 1. Okay, 1 over L times L is just 1. So we'll get the natural log of L minus y, and then that will equal the integral of k, again, will be kt plus c. All right, one thing that I'm going to do, just because I want this problem to work out nicely, I'm going to multiply through by negative 1 before I try to simplify that at all. So I'm going to get negative natural log of y minus, or actually that will turn to plus, natural log of L minus y is equal to negative kt plus c. The next thing that I'm going to do on the left side is put my ln's together, so it's going to be ln. Since the L minus y is positive and the y is negative, the L minus y is going to go in the numerator. So I'm going to get L minus y over y, and that's going to equal negative kt plus c. Just like we did in the previous problem, we're going to go ahead and do the logarithmic loop. And when I do that, I'm going to come up here now. I'm going to get L minus y over y is equal to c e to the negative kt. I still need to solve for y. So I'm going to separate the numerator on this one. That will give me L over Y minus 1 is equal to C e to the negative kt. Still in my quest to solve for y, I'm going to add 1 to both sides. So now I'll have L over Y is equal to C e to the negative kt plus 1. And then the next thing that I'm going to do is multiply both sides by y. So I'm going to get L is equal to C e to the negative kt plus 1 times y. And then to get y by itself, I'll divide by what's in my parentheses. So I'm going to end up getting y is equal to L over C e to the negative kt plus 1. Okay, so that is my logistic equation. So now instead of having to do this long process every time, unless I specifically ask you to do the long process, we can go straight from our differential equation. We can take some pieces from it to come up with our logistic equation, so we don't actually have to go through that process every single time. All right, and we're going to go ahead and now do an example. This one says to solve the logistic differential equation, dy dt equals 1.2y times the quantity 1 minus y over 8 with the initial condition 0, 5. So please keep in mind that we had y is equal to L over C e to the negative kt plus 1, and we started out the differential equation was dy dt equals ky 1 minus y over L. So we're going to try to pull pieces from the differential equation to help me with this. So I notice just by matching up parts of the formula that k is going to be 1.2, and I also notice that L, the carried capacity, is going to be 8. So my formula will look like y equals 8 over C e to the negative 1.2t plus 1. Okay, now all I need to do is figure out my c. They did give me an initial condition to figure that out. So I'm going to have 5 equals 8 over C e to the negative 1.2 times 0 plus 1. So I'll get 5 equals 8 over e to the 0 will end up being 1, so I'll end up getting c plus 1. If I cross multiply, I'll get 8 equals 5 times the quantity c plus 1. I'll then divide by 5, so I'll get 8 fifths is equal to c plus 1. Then I can subtract 1 from both sides, and I'll end up getting c equals 3 fifths or 0.6. So when it asked me to solve the differential equation, I came up with the equation y equals L, which was 8 over 0.6 e to the negative 1.2t plus 1. There we go, we solved it.